Hello everyone, welcome to this lecture on debugging and understanding deep learning models. In this lecture, we will dive deep into different types of model understanding tools, techniques, and their practical applications. I'll start the lecture with a brief introduction of model interpretability, explainability, and the desiderata of interpretability. Then we will talk about the differences between explaining black box models and building inherently interpretable models, followed by an introduction of gradient and perturbation-based explanation techniques and their practical applications for image classification and segmentation. In the second part of the lecture, I'll introduce concept-based model interpretability and a specific algorithm from this area of research. In the last part of the talk, I'll introduce different types of model comparison techniques and show how they can be used to understand model internals. Lastly, I'll recap the lecture with a brief summary and talk about new exciting research areas in model understanding. The definitions of interpretability and explainability in AI are rather elusive, and the line between those two concepts is blurry and often not well defined. Some researchers use these two concepts interchangeably, and some call anything that tries to explain pre-trained models as explainability. I'd like to start with some definitions for the scope of this lecture that will help us to better understand those two concepts. Explainability seeks answers to why question about the decisions and behavior of our model. Interpretability describes AI model internals and their predictions in human understandable terms. In some sense, interpretability helps us to explain the model and can be seen as a subset of the larger explainability concept. In a general sense, both interpretability and explainability aim to increase the understanding and trust in our models, and in this talk we will use those concepts interchangeably. If we don't have access to the internal workings of a model and we don't know how the model makes predictions, then we call that model black box, as also visualized on this slide. Let's say that we are given a black box model and we are told that this model is making accurate predictions. The only way we can test the correctness of model is by looking at the prediction scores and by comparing models' prediction output with the ground truth labels provided by the humans. Based on this, we can estimate accuracy and model performance metrics. However, it is still not sufficient to characterize the model and tell how exactly model came to the prediction. For those reasons, we need a mechanism to look into internal workings and understand how the model came to the final conclusion while making the prediction. Those mechanisms and techniques are called explainability or interpretability techniques. When we generate interpretations, we want to have a list of properties, also known as desiderata, that those interpretations will satisfy or conform with. Here we list all 5 desiderata for model interpretability according to a highly cited paper in the model interpretability community. The 5 properties associated with the desiderata of interpretability are trust, causality, transferability, informativeness, and fair and ethical decision making. We'll go over each of them in the next slides. One might say that we want that our interpretations convey trust. But what do we actually understand by saying that we trust a model? Is this the confidence about model performance? Model performance can be different in different deployment environments and different data distributions. And we can't expect our models to account for all kinds of biases in our data. One might define trust as how much model's output is aligned with our humans' expectations. And expect the model to be right when we humans are right. In the cases when we and the ML models are wrong, we can have human supervision of those algorithms. The second desiderata is causality. So ML researchers and engineers often use ML models to draw causal relationships between the output prediction and input features, such as smoking and lung cancer. One might think that ML interpretability should help us to infer such causal relationships between associated variables. But we have to be careful that these methods rely on strong assumptions and not always those assumptions are met. The third desiderata is transferability. This is another property that we desire for the interpretability, and we want that we are able to assess the generalizability of our models and how well those models adapt to new environments. Usually we relate generalizability to the model performances, error differences between train and test datasets. But oftentimes, test and train datasets come from the same distributions. So in some sense, that error doesn't necessarily describe the true generalizability of our model. Another criteria is that the models often can be fooled by adversarial attacks. There are many situations where humans wouldn't be fooled, but the machine does. Adversarial robustness is another property that we would like to see for our models. The fourth desiderata is informativeness. Most black box models convey information to users about their decision making through the output of the model, which oftentimes is a single prediction score. Ideally, we would like to have more insights and description about the decision of our model. For example, the system can point out to the examples that are similar to the predicted one, and this can help the users to understand better why the system made the decision. Lastly, the fifth desiderata is fair and ethical decision making. So this is another aspect of interpretability where we would like to tackle whether our model makes fair predictions. This is especially critical when AI decisions get more incorporated into healthcare and social experiences. For example, courts rely on AI predictions for recidivism and other critical matters in human life. Lately, more regulations in algorithmic decision-making have been made that require decision-making to be grounded by the interpretations and reasoning why the prediction was made a certain way. Some regulations see algorithmic decision-making contestable, that they can help to contest propositions and modify decisions. So far, we had been talking about black box models and explaining or interpreting black box models, but now let's talk a little bit about models that are inherently interpretable. So we would like to compare and contrast these two types of models. So let's start with explaining black box models. So for explaining black box models, we also this technique we call it post hoc interpretability in the literature, and we say that it aims to infer behavior of a pre-trained model by perturbing the inputs, by looking at gradients during backpropagation and doing some visualizations of the input features or the internals of our models. So when we explain black box models, we do not need to train a model and change any internals of the models. There is no predictive performance sacrifice for this type of model explainability or interpretability techniques. So in case of inherently interpretable models, it is clear how the model came to the decision. So there is no need to use additional algorithms such as input perturbations or looking at gradients in order to interpret the output of the model. For example, decision trees or linear models are examples of inherently interpretable model. When we look at the output of a decision tree, we can clearly understand how the system made decisions. This is more challenging for deep neural networks because deep neural networks are known to be primarily black boxes. Nonetheless, there still exist techniques such as prototype networks that rely on similarity estimates during the learning and explain the decisions on the basis of the similarity of the predicted images to a large collection of learned image prototypes. This type of models might take a lot more effort to design and train, and they might require performance sacrifice, but their predictions are more interpretable. So starting from here, we would like to focus on deep learning models and focus on explaining and interpreting deep learning models that are black box, since the majority of deep learning models are considered to be black box. In order to explain black box models, there exist two types of algorithms. Those are gradient and perturbation based algorithms that help us to understand the model internals and estimate feature importance score using attribution techniques. So the attribution techniques help us to attribute output predictions to the inputs of the model and attribute to output predictions to neurons and layers, and this way understand what's more important for specific prediction. So let's start with gradient-based methods. So gradient itself describes an infinitesimal change in the input that changes the output of the model function. Hence, it serves as an explanation of the output change on the basis of subtle input feature perturbations. In order to compute the gradients, we need to call forward and backward passes in PyTorch. Most gradient-based methods require one forward and one backward pass for each input example. In contrary to gradient-based methods, perturbation-based techniques do not require backward passes and gradients, but they require multiple forward passes. Perturbation-based methods look into the differences of models' output changes when the input values are perturbed for each input feature in the input X. Feature ablation, permutation, Shapley values, Lime or Corner-Sharp are examples of it. And later in this lecture, we will look into different approaches for perturbation-based methods. So now let's look into the details of several gradient-based techniques. One of the most simplistic gradient-based methods for the explanations is the gradient of model output for a specific class, or the output if it's a scalar, with respect to model inputs. In the literature, it is also called saliency. So as we mentioned in the previous slide, saliency explains the output predictions on the basis of infinitesimal input changes. On my right side of this slide, we can see an image that was predicted as plain using a model that was trained on CIFAR dataset. Here we visualize the magnitudes of gradients overlaid on the original image. Larger magnitudes, highlighted in dark blue, indicate strong prediction signal for the plain class. Gradients have some limitations, and some of them are that they can be noisy, they are sensitive to functions inputs, and they are not always faithful to function outputs. This means that although inputs can be very close to each other, the gradients for those inputs could lie very far apart from each other. A technique called smoothgrad helps us to mitigate that issue of noisy gradients by adding Gaussian noise to input samples and computing the expected value of explanations in the neighborhood of input x. In other words, this technique performs smoothing by approximating with Gaussian kernels. On my right side of the slide, we can see the magnitudes of the attribution maps overlaid on the plane image. We can see that in this case, we see much stronger important signal in dark blue highlighted on the body of the plane. Smoothgrad also has some limitations, and some of the limitations of this approach are that finding an optimal number of sampling can be challenging. Also, it can be computationally more expensive if the number of samples that we sample in the neighborhood of input x is large. So integrated gradients is another technique built on top of gradients that helps us to explain the predictions of our model, and it computes the gradients along a straight line from baseline to input. So let me explain in more detail what that means. So first, baseline. Let's define baseline. Baseline oftentimes represents an uninformative input which is compared and contrasted with the original input in order to draw conclusions about the features that stand out or are more important in the original input. In this case, the baseline on this slide, we have a black image and the original input is a plane. So the baseline doesn't have to be black image. In case of images, it can be white image, or it could be the average of white and black, or it could be also a random image. In case of integrated gradients, we integrate the gradients along the straight line across all n samples from baseline to input. Formally, it looks something like this. We use alpha scaling factor that helps us to choose a point between baseline and the input, and we integrate from 0 to 1. In order to compute the integral, we can use Riemann sum, for example. Some of the limitations of integrated gradients is that finding good baselines can be challenging, and integrated gradient does not account for feature correlations and interactions. Integrated gradient satisfies a number of important axioms or has a number of interesting properties that I would like to mention. One of them is the axiom of the completeness, which states that the sum of the attributions is equal to the differences of our neural network's function at its input and baseline. This axiom is closely related to the fundamental theorem of calculus for path integrals. So the second axiom is the axiom of sensitivity, which states that if the input and the baseline differ at one feature and result to different prediction scores, then for that different feature, we will have non-zero attribution. The third axiom is implementation invariance, which states that the attribution for two functionally equivalent DNNs is identical. Apart from silency, smoothgrad, and integrated gradients, there are also a number of gradient-based methods that modify the gradients during backpropagation and propagate important scores instead of gradients. The algorithms in this category include deep lift, LRP, guided backprop, GradCam, guided GradCam, or deconvolution. Let's look deeper into one of those approaches, namely deconvolution. Let's assume that we are given a deep learning model that has ReLUs in some layers as depicted on my right side of the diagram. We also visualize forward paths for the ReLU activation. During backward pass, the convolution passes through only non-negative gradients, as also visualized on this example. So it modifies the gradients the way that only positive gradients are passed through the network, and this helps to focus on the part of the input that is more discriminative for reconstruction of the input. Some of the limitations of gradient-based methods that modify the gradients during backpropagation are proven to be insensitive to model parameter randomization, except deep-leaf algorithms. This means that the methods do not necessarily provide faithful explanations, and even if we randomize all weights in our network, their explanation will not change. I linked the paper that discusses the proof for this on this slide. Now let's look into the details of several perturbation-based techniques. One of the most simplistic perturbation-based approaches is feature ablation. Feature ablation measures the importance of input features based on the magnitude changes in the prediction scores or measures of prediction goodness when features are ablated. Let's look deeper what this means and how we ablate the features. In order to ablate features, we define feature masks. Feature masks help us to define groups of features that we want to ablate together, as shown on this slide. Here we want to ablate first and third features together. To do so, we use the same feature ID for first and third features. Besides feature masks, we also define ablation values, also known as baselines, that are used to replace the original feature values. Traditionally, zeros are used as ablation values, but we can also define custom ablation values. Formally, example-based feature ablation can be defined as differences of our neural network functions output without and with ablation. Here, feature masks are defined and denoted as M, and ablation values are denoted by B. We can also use feature ablation for a dataset in combination of a loss function or a performance metric, such as accuracy, and also use human labels. In this case, feature importance for dataset X is defined as the differences of our loss function L without and with feature ablation. As a loss function, we can use accuracy, mean squared error, or any other metrics that we desire. Occlusion is another feature perturbation technique that is built on top of feature ablation. It ablates rectangular patches of inputs using a sliding window and estimates the importance scores as differences between the model function output without and with ablation. This method is very popular in CV community for images, but it can also be used for other applications. Some of the limitations of feature ablation is identifying which features to ablate together and what ablation values use. Besides that, the ablated features might be out of test, train, or valid data distributions, and this could lead to model predictions that have high uncertainty scores. If we have to ablate many features in a sequence, then this can also be computationally expensive, so this is another limitation that we need to take into consideration. Another perturbation-based attribution algorithm that is designed to explain and interpret black box models is LIME. LIME approximates the predictions of a black box model using an interpretable surrogate model such as a linear model or a decision tree. In the next slide, I'll describe the inner workings of LIME. Let's assume that we are given a black box model F that takes input x, and let's assume that our input x has n features that are denoted as f1 to fn. Now let's specify an interpretable representation of those features using binary codes that indicate whether the feature is present or not. We will denote this representation as x prime. For images, this can indicate the presence or absence of some patches on the image. For text, this could indicate the presence or absence of some tokens in the text. Given x and x prime, as next we draw n samples uniformly random in the neighborhood of input x prime. Those are the perturbed input samples visualized with a cross symbol in the neighborhood of x prime. Let's denote the set of those sampled inputs in the neighborhood of x prime as z prime. As next, let's assume that we are given a transformation function hz that helps us to convert interpretable representation into the original representation. So this function helps us to convert the samples z prime into the samples z in the original input representation. Now let's define a similarity function pi that helps us to compute the similarity between given sample and the sample sampled in its neighborhood. We can compute the similarity both in the interpretable and original input spaces. For lamp specifically, we compute the similarity in the interpretable input space. We can use any similarity function of our choice. Typically, for text, we use cosine similarity, and for images, Euclidean distance. Now let's define our interpretable surrogate model, G, that takes Z prime interpretable inputs as input to the model. We can train a surrogate interpretable model. In this case, we have a linear classifier that learns to discriminate between different classes for the Z prime input samples. From one side, we have interpretable model G Z prime, and from other side, we have our black box model FC. So our goal is to minimize the weighted distance between black box and interpretable surrogate linear model. And when we minimize our L function helps us to estimate the approximation, and the minimization of the L function helps us to estimate WI parameters for our G interpretable model, which serves as importance scores for interpretable features. As we can see, I denoted the importance score as WIG to WNG for all our interpretable features. Similar to other techniques, LAM also has some limitations. It depends on the choice of sampling technique, sample size, and similarity function. Besides that, it also heavily relies on the accuracy and complexity of the interpretable model. Shapley values is another technique that helps us to compute feature importance. It is a perturbation-based technique that has been adopted from cooperative game theory and measures expected marginal contributions of input features for given prediction. Now let's look deeper into this and understand what does this mean. In a cooperative game theory, during each game, the players form a coalition in order to receive a profit from that corporation. Shapley value helps us to send payouts to each player from the total payout, depending on the contributions of the players in the game. If the player had big contribution, then they will receive big payout. If they had smaller contribution, then they will receive smaller payout. Shapley value uses a fair approach to assign payouts to each player depending on their contributions in the game. For example, on this slide, we have 3 players, Alice, Bob, and Mary, that are dividing between each 3 of them the total payout of $20. So using this information, we can make an analogy between input features and players in the game, where our goal is to assign a payout contribution score to each feature, which can ultimately also serve as an important score. Each data sample in our dataset with specific feature values could be represented as a game collision, where each feature is a player, and our goal would be to assign contribution scores to each feature in that example. In order to understand this, let's look into it in more detail. Let's imagine the following example. Let's say that we have a model that helps us to predict house prices based on 3 features: house age, the number of rooms in the house, and the house location. Let's imagine that we have a house in our dataset that is 40 years old, has 3 rooms, and is located in downtown San Francisco. Our model predicts that the price for the house is $500,000, and we would like to understand which of those 3 features, age, number of rooms, and locations, have contributed to that predictions, and how much were the contributions of each of those features. In order to make the explanation easy, let me assign feature IDs to each feature. So age will have feature ID 0, room 1, and the location 2. And using these feature IDs, we would like to define possible orderings of permutations for all these features. Since we have 3 features, then we will have total 6 different permutation orderings of input features. Let's look into each of these permutation orderings. Let's start from the first permutation. So in the very beginning, when none of those features contribute to our predictions and their value is empty, we would like to compute the function value for the case when none of the features is empty. And this will also define for us a baseline. So we denote that baseline for permutation 1 out 0_1. So then, according to the orderings in permutation 1, we update the feature values. And so according to this ordering, the first feature that we would update is the age. So when we update the value for the age, we receive feature ordering 40 years, empty, empty. And we compute the function output for this combination of inputs. Then according to our permutation, we update the next feature, which is the number of rooms, and this will and for this as well, we compute function output when we have 40 years, 3 rooms, and empty, location is missing. And lastly, we add our last feature and compute feature values when all 3 features are empty. All features are present. Based on the output calculations of permutation 1, we can compute feature contributions for all 3 features. So for all 3 features, feature contributions are computed as the differences of function output after the feature is added and before the feature is added. So as we can see from the first permutation, we can already assess some feature importance and contribution scores for all 3 features. Next, we will move to permutation 2 and repeat the same procedure that we did for permutation 1. we'll again define our baseline when all our features are missing. Then we will start adding features in the ordering specified in the permutation 2. So according to our permutation 2 ordering, the first feature that we need to add is number of rooms. So we add number of rooms, 3 rooms in our feature sequence, and we will compute output for empty, 3 rooms empty. Then we move to the next feature and update the age, compute the output for this, and then lastly we compute the function's output when all features are present. Similar to previous case, we compute the contributions for the permutation 2, which is again the differences of the function's output after the feature is added and before the feature is added. So far we have computed feature importance contributions for permutation 1 and 2, but we can do that for all 6 permutations. And when we do it for all 6 permutations, we receive contribution scores for each permutations, in this case 6. And in order to compute Shapley value and the final contribution score, we sum up the contributions for all 6 permutations across all 3 features and normalize that score by the number of permutations, which in this case is 6. So that was an example of Shapley values. Now let's look at its formal definition. So according to its formal definition, Shapley value for the feature I, xi, is defined as the aggregation of functions output when output differences when the I feature is present and it's missing across all subsets of S in N, where N is the number of all features. And this is also weighted by the number of all combinatorial variations of the subsets. Some of the challenges of Shapley values, as we can also guess, is the computational cost. It is especially expensive if the number of features is large, because it is exponential in the number of input features. In order to mitigate this issue, we can only use randomly sampled subsets of permutations. This is what Shapley value sampling algorithm does, and I also linked that algorithm on this slide. You can read more about it. Shapley value has some useful and interesting properties, and I would like to talk a little bit about them. One of those properties is symmetry, which states that for any function f and all subsets S that do not contain I and j features, if I and j are interchangeable, then the function's value at S, including I, is equivalent to function's value at S, including j. The next axiom is called dummy, which states that for any function f and all subsets S that exclude I, if I is the dummy feature, then f's value at S is equal to f's value at S plus I. The next property is called additivity, which states that the attributions of the linear combination of two functions f1 and f2 is equal to the linear combination of attributions for each of two functions. So in order to reduce computational costs for Shapley values, another new technique has been developed, which is called SHAP. SHAP stands for Shapley Additive Explanations. SHAP approximates Shapley value by computing the conditional expectations of feature contributions instead of the marginal contributions that the Shapley value is computing. So in order to understand SHAP, let's define couple variables that we would like to use in the explanation. So first we will define x prime. X prime, similar to lime, it is an interpretable representation of input x. It also has a binary representation indicating whether the feature is present or not. Similar to lime, here as well, we define an interpretable explanation function g that takes x prime as inputs. And analog to lime, here as well, we have a transformation function hx that helps us to transform inputs in the interpretable input space into the original input space. So SHAP has an important property called the additivity property that states that our interpretable model Jx prime is linear model, and it represents linear combinations of the product between our explanation and the input. Now let me to introduce a couple more notation in order to be able to explain SHAP fully. So let's also introduce the set S, which is a set of non-zero indices in Z prime, and ZS has missing values that are not in S. Let's also define a set Z complement, which is a set of features that are not in S, and ZS complement has missing values that are not in S complement. So with ZS and Z complement, we are defining two sets that contain features that are missing in one but are present in other set. We can approximate the value of fxz as the expectation of the fz given the zs set of missing features. After we do several definitions and formulations, you can read the details in the paper. We come finally to a conclusion that fxz could be approximated as the function of FCS samples where the missing features are replaced by their expected values in Z's complement subset. Lastly, after we have FC estimated using conditional expectation, we can use an approximation technique similar to LAM to minimize the distance between the original FZ and interpretable model JZ prime. Here, the similarity matrix pi is computed based on the combinatorial variations between the interpretable input features and the number of non-zero inputs in the interpretable input Z prime. In this part of the lecture, let's look into the practical applications of attribution algorithms. Before we start with the practical applications, I'd like to introduce a model interpretability library for PyTorch models called Captum. We will use this library to perform gradient and perturbation-based attribution computations for classification and segmentation tasks later in this lecture. The library has three main characteristics. The first characteristic is multimodality. This means that we can use the library for any type of PyTorch models and inputs stemming from different sources, whether it's text, image, or any other modality. Second characteristic is extensibility, which means that we can easily extend the library and add new techniques from the state-of-the-art literature. And lastly, the third characteristic is ease of use, which means that the library is designed to be used easily with a couple lines of code. The library is open source and available to everyone, and it offers a number of gradient and perturbation-based attribution algorithms and evaluation metrics. The attribution algorithms can be grouped into three categories. The first category of attribution algorithms, also known as primary attribution, allows us to attribute an output prediction to the inputs of the model. These attribution algorithms are also known as feature importance algorithms, such as LIME, kernel-shape, integrated gradients, or feature appellation. The second category of the attribution algorithms, also known as layer attribution algorithms, allow to attribute an output prediction to all neurons in an internal layer. These approaches oftentimes represent slight variations of the feature importance or primary attribution algorithms and are applied to an internal layer of the model instead of the inputs of the model. Lastly, the third category of the attribution algorithms, also known as neuron attribution, allow us to attribute an internal neuron to the inputs of the model. These are very similar to feature importance algorithms, with the only difference that instead of attributing the output, we attribute an internal neuron to the inputs. On this slide, we summarize all attribution algorithms in Captum library. Some of these algorithms I've already introduced in deeper details in my previous slides. For example, LIME, integrated gradients, or feature appellation, to name a couple of them. The perturbation-based approaches are highlighted in pink, gradient ones in purple, and the ones that do not belong to any of those two categories are highlighted in dark blue. On my left side of the diagram, we see the list of attribution algorithms that allow us to attribute the output predictions or internal neurons to the inputs of the model. These are also primary and neuron attribution algorithms. On my right side of the diagram, we can see the list of the algorithms that allow us to attribute output predictions to all neurons in an internal layer. These are also known as layer attribution algorithms. In the next slides, I'll showcase how we can apply some of these algorithms to our segmentation and classification models using Captum library. Now let's apply some of those algorithms from Captum library to well-known pre-trained models. Let's assume that we're given a black box model that was trained on CIFAR dataset. Let's also assume that we are given an image of a plane and our black box model is able to correctly predict that there is a plane on the image. We are asked to identify which features and internal layers and neurons are important in predicting the plane object on the image. Here we provide code snippets showing how we can compute feature importance scores using saliency algorithm from Captum library for the prediction of a plane on the image using a model trained on CIFAR dataset. To do so, first we import saliency algorithm from the captum.attr package. Apart from that, we also import a visualization component from the same package that will help us to visualize important pixels on the image. As next, we create an instance of the attribution algorithm using forward function of our PyTorch model. In order to compute attributions, we call attribute on the instance of the attribution algorithm by passing the input image and the target index, which in this case is the plane index. In order to visualize the feature importance scores, we call visualize_image_attr module on the visualization component and pass the attribution scores, original input image, and other optional arguments for the visualization. On my left side of this slide, we can see the attribution scores overlaid on the original image. The darker the color, the more important the features are for the prediction. We see some important pixels on the body of the image, but also some on the sky. It seems like sky background has also contributed to predicting plane object on the image. Now let's try another algorithm, namely integrated gradients. Similar to saliency, we import integrated gradients from Captum library and create an instance of it using forward function of our model. Then we compute the attributions and visualize them using the same code snippet that we used for saliency. When we visualize the attributions, we can see that the attributions have both positive and negative scores. Positive scores are highlighted in green and the negative ones in red. Positive means that those pixels are contributing to the prediction of the plane class, and negative means that those pixels are contributing to non-plane class, so it could be any other class. In this example, we can see that most negative pixels are in the sky, which means that those pixels aren't related to the plane, whereas those on the body of the plane have darker intensities of green color, which means that those pixels on the plane are important in predicting the plane object on the image. Now let's use a layer attribution algorithm, namely layer integrated gradients, in order to better understand what different layers in our model learn. Similar to integrated gradients, we import layer integrated gradients and initialize it using the forward function of our model and an internal layer for which we would like to compute the attributions. In this case, we chose the first convolutional layer, conv1. We then compute the attributions for the layer and interpolate those attributions to the image size so that we can visualize them. Now we can visualize attribution scores for conv1 layer and examine what important features the layer learned, highlighted in green and red colors. Similar to layer integrated gradients, we can also compute neuron integrated gradients using an internal layer. In this case, we also chose the conv1 first convolutional layer in the CFAR pre-trained model. When we call attribute, we also need to specify a neuron index, or alternatively also a function that takes all neurons in given conv1 layer and performs an operation on it. In this case, we attribute the sum of all neurons in the conv1 layer to the inputs of the model. Here we can see interesting patterns when we visualize the attribution scores for all neurons in the conv1 layer. It is interesting to see that some parts of the plane appear unimportant for the conv1 layer and that the edges of the image are also negatively correlated with the plane prediction. We can use the same procedure for the Shapley value sampling algorithm. As we can see from the visualization, Shapley value is able to identify important pixels on the body of the image and clearly sees the sky as unrelated to the plane prediction. In a general case, we can use any algorithm from Captum library to create an instance by creating an instance of them and calling attribute on that instance by passing the inputs, the target class prediction, and other necessary inputs for specific algorithm implementation. Now let's look into a case study for brain MRI segmentation and use Captum library to identify important pixels in predicting abnormalities on MRI scan. A brief description about the model and the dataset. The model architecture used for this case study is UNet. The model was trained on an MRI segmentation dataset, which also has FLAIR abnormality segmentation masks available. On this slide, we see an input image of an MRI scan with an abnormality on it that is used to make a prediction using pre-trained UNet model. On the right side, we can see that the model was able to predict the abnormality. Here we visualize the input prediction, the contours of the predicted abnormality, and the ground truth mask labeled by humans. As we can see, the prediction is quite close to the ground truth label, which was provided by humans. As next, we would like to use integrated gradients algorithm to identify which input pixels on the image are important in predicting the abnormality segment. To do so, first of all, we need to load pre-trained UNet model. Since there already exists a unit model on torch.hub, we can load it from there with one command line. After loading the model, we would like to define a function that will help us to summarize the predictions in the output segment. This will help us to attribute total sum of prediction scores to the input of the model instead of attributing each input pixel at a time. We could do that too, but in that case, we would need to attribute each of those pixels to the input. Now let's import integrated gradient algorithm and compute attributions using our input tensor. It's important to note that the input tensor, the image with the abnormality on it was normalized using channel-wise mean and standard deviation, similar to the original training dataset, which was used to train the model. After computing integrated gradients, now we can visualize the attribution scores. On the bottom left of this slide, we can see the original image and corresponding attribution maps. Light colors mean high positive attribution scores. In this example, we can see that in the area of abnormality, we observe important pixels that contribute to the prediction highlighted with white dots and concentrated in the area of abnormality. Now let's try another algorithm, namely guided backprobe instead of integrated gradients. Similar to integrated gradients, we visualize the attribution scores for the predicted segment, and when we visualize it, we can see that the pixels on the abnormality area are even more visible, and we can see that this algorithm is able to show more pixels that are important for the prediction of abnormality. Now let's try a layer attribution algorithm and see what the layers learned about the abnormality area. In order to work with layer attribution algorithms, we need to define a wrapper PyTorch model that wraps original unit pre-trained model, and in the forward function returns the sum of the predictions for the abnormality segment. Let's say that we want to know what our convolutional layers learns, and more specifically, we choose the upconv4 layer. So in order to understand what this layer learns for our prediction of abnormality, we pass it to as an argument to the instance of layer gradcam algorithm together with the instance of our model. And then we compute the attributions similar to what we did for integrated gradients. So in order to visualize the attribution scores for a layer, we need to interpolate the scores to match the size of our input. After we interpolated the attribution scores and we have now output that has the same size as the image, we can visualize them using the same functions that we used for integrated gradients. On this slide, we can see what upconv4 layer learned. We can see that it has high attribution score, close to 1, especially in the area of abnormality. We can do this, we can repeat this procedure also for other layers and other neurons in order to understand what part of the image do different layers and neurons focus on. In this section of the lecture, let's discuss how to evaluate the goodness of interpretability. In other words, let's see how and if we can estimate the reliability of our explanations and interpretations. As we can imagine, the evaluation of model interpretability is challenging, and there is no clear guidance on how to quantify the quality of interpretations and explanations. Although recently new quality quantification metrics and sanity checks have been developed, most of them are domain-specific or are based on specific properties of an algorithm and measure only certain aspects of the interpretability. Apart from that, although visual explanations can be helpful, they can also be misleading, and often they are seen as confirmation bias, especially in the images. In the pursuit of finding different ways of performing model interpretability evaluation, two researchers from the model interpretability community have defined a taxonomy of interpretability evaluation. This includes different levels of evaluation, starting from automatic to manual, where human experts get involved. Let's start from the bottom of the taxonomy. In the bottom of our taxonomy, we have functionally grounded evaluation. This type of evaluation doesn't require any human involvement. Quality assessment is performed by a proxy task, which is an automatic evaluation based on a software. Examples of such evaluation can be quantifying the depth of the tree or performance improvements for the interpretable model. Identifying good proxy tasks can be very challenging and is still an open field of research. The second type of evaluation approaches in the taxonomy is human-grounded evaluation. This type of evaluation requires human involvement, but the humans do not need to be domain experts. In this case, besides human evaluation, we also perform an automatic evaluation using simple proxy tasks. The last third type of evaluation approach in our taxonomy is application-grounded evaluation. This type of evaluation requires that the explanations are validated by end users and domain experts. It requires to define how to evaluate quantitatively in an unbiased manner and is the most costly and specific evaluation. An example of this type of evaluation is when, for example, the model developers work closely with a domain expert, such as doctor, to diagnose a disease. In the bottom of the taxonomy, we have the list, and on the top, we have the most specific and costly evaluation techniques. Now let's talk about some quantitative evaluation metrics. Sensitivity max is one of those metrics. Sensitivity max is a metric that estimates the quality of explanations in terms of explanation sensitivity to subtle input perturbations using Monte Carlo sampling-based approximation. Given an input x, its perturbation y on the radius r, a neural network function f, and an explanation function phi, sensitivity max is defined as the maximum distance between the attributions with and without perturbation normalized by the norm of the explanations without perturbations. Lower sensitivity max scores means that our explanations are more robust and less sensitive to subtle input perturbations on the radius r. Similar to sensitivity max, infidelity is another metric that measures the quality of explanations. This is a generalization of the completeness axiom, which we already got to know from integrated gradients algorithm. Given an input x, a neural network function f, a meaningful perturbation I with a probability measure mu I, infidelity is defined as a mean square error between dot product of input perturbation and explanation and the differences between the predictor function at its input and perturbed input. Ideally, we would like to have a lower infidelity score. The lower the infidelity score, the more trustworthy the explanations are. Both infidelity and sensitivity max metrics are available in Captum library. For the real use cases, I would advise to look into the original paper and Captum paper available on the archive. There are other domain-specific metrics for computer vision and other domains that have been developed over the years, but we will not discuss them in this lecture. Yet, I'll advise you to check state-of-the-art literature for any new metrics on evaluating the quality of model interpretability. Now let's look into a different area of model interpretability research called concept-based model interpretability. Concept-based model interpretability aims to explain model predictions by the means of abstract concept representations. Let's define visual concept representations that can help us to explain model predictions. In this case, we have examples of two concepts, straps and random. The concept of straps resembles a number of examples that contain strap object in any possible context. It can be straps on the t-shirt, zebra, pumpkin, or crosswalk. The second concept is random concept. In contrast to straps concept, random concept doesn't resemble any specific high-level concept. That's why it is called random. Note that concept representations do not have to be visual. They can be in any other form and shape. We chose visual representations because it's easy to explain ideas with them. Concept-based model interpretability helps us to measure the sensitivity of model predictions to different high-level concepts, such as straps or any other concept that we choose to. Now let's assume that we are given a number of zebra images and a predefined model that predicts what animal is depicted on the picture. Let's assume that when we perform prediction on the zebra images, our model most of the time is able to correctly predict zebras. However, we still don't know how exactly our model made that decision. We don't know what part of the images were important for the prediction. Let's assume that we have predefined sets of concepts such as straps, and we want to know whether the straps on zebra played any role in predicting zebra. Testing with concept activation vectors, TCAV, is an algorithm that belongs to the family of concept-based model interpretability approaches and can help us to solve this problem. TCAV helps us to test the sensitivity of different model layers to model prediction. TCAV algorithm consists of two steps. The first step is the generation of the CAVs. The second step involves directional sensitivity computations. Let's go over each of those steps and understand how this two-step procedure can help us to perform concept-based model interpretability. First, let's understand what CAV means and how we can generate them. Let's assume that we are given a multi-layer neural network that performs classification. In this example, we have a deep neural network that takes n features and outputs a class index between 0 and p. Let's select a layer in this model and call it L2. Let's also assume that we are given a FL function which computes the activations in the layer L2 and HLK function that takes activations in the layer L2 as inputs and produces output of our model. In order to compute concept activation vectors, let's first compute the activations for all our concepts that we have in a given L2 layer. In this case, let's compute activations for strap and random concepts. Concept activation for each concept represents the output of FL function for each image that resembles either stripes or random concept for this specific example. Now let's train a linear classifier that helps us to distinguish between those two classes of concepts, stripes and random. Concept activation vector, also known as CAV, represents the vector that is orthogonal to the hyperplane that separates those two classes, stripes and random. For stripes, the CAV vector is orthogonal to the linear hyperplane and points towards the stripes concepts. For random concepts, CAV vector is also orthogonal to the hyperplane but points towards the opposite direction. Note that binary class problem in this case is just an example. In a general case, we can have more than two concepts and more than two classes. After computing the CAVs, let's move to the second step and compute directional sensitivities. Let's recall from the previous slides that our goal is to identify which concepts are important for predicting zebra object on the images. For those reasons, we would like to understand the sensitivity, that is the gradients, of the output zebra prediction with respect to the output of our L2 layer. This is exactly what we do in the step 2. We denote the gradients of output zebra class with respect to output of layer 2 as sense subscript L superscript zebra. As next, we combine the outputs of those two steps, CAVs and directional sensitivities, together with a dot product, which results to a CAV_sense vector that describes the sensitivity of each zebra image to the stripes concept in the layer L2. In order to compile and create one quantitative score and aggregate CAV_sense scores across all images, we divide the number of images with positive set CAV_sense scores with the total number of zebra images. In other words, TCAV represents the fraction of images for which the sensitivity direction is aligned with the CAV direction. In a general case, TCAV score for a given class, layer, concept, and input images is equal to the fraction of examples for which CAV and directional sensitivity vectors are aligned and are non-zero. It's important to mention that TCAV can potentially learn meaningless CAVs for meaningful concepts, depending on the biases in our concept dataset or the linear model that learns the CAVs. Also, it can happen that a CAV generated by the random concept can be meaningful depending on the random concept dataset. In order to mitigate those issues, we can test statistical significance of our concepts using two-sided statistical significance tests. We can do that, for example, by testing a specific concept, for example, stripes, against many random concepts. If stripes concept is really meaningful, it will stand out with high TCAV score among all random concepts. Now let's discuss some of the limitations of TCAV algorithm. TCAV requires predefined concepts. As we saw in our previous slides, we had to have a predefined set of stripes and random concepts. This could potentially require some human labor, but it would be great if we could generate them automatically. Another problem is that the CAVs can be meaningless, as I mentioned in the previous slides. And we also saw in the previous slides that two-sided significance tests can help us with that, but for that we need to compute TCAV for a large number of experimental sets of concept and random images, and this can be computationally and memory intensive. It's also important to note that this algorithm will be available in the next release of open source Captum library. TCAP is one of the approaches in concept-based model interpretability research. There are a number of other publications in this area of research. For example, one of them is trying to automatically extract concepts from images. This can help with the limitation of having a predefined set of concepts. Another recent publication aims to identify a sufficient set of concepts that describe our prediction. It adapts SHAP algorithm to concepts in order to identify most important and influential concepts. In this part of the lecture, let's discuss different types of techniques that can help us to understand and visualize the internal layers of a model and compare them across different pre-trained models. Before looking into how to compare layers, let's look into the individual layers first and try to visualize and understand them. As we all know, layer activations of a neural network are high-dimensional vectors. Therefore, it is challenging to visualize those high-dimensional vectors. Principal component analysis, also known as PCA, helps us to reduce the dimensionality of our high-dimensional embedding vectors. It projects high-dimensional embedding vectors into a lower dimensional space that captures maximum variance in the data by converting a set of possibly correlated variables into a set of linearly uncorrelated variables. PCA components can be sorted based on the amount of the variance that they capture. On this example, on the bottom right side, we visualize two top principal components, PC1 and PC2. On this slide, we visualize top two principal components for a real dataset and model. In this case, we used CIFAR10 dataset and a model that was trained also on CIFAR10 dataset. The colored dots represent the samples from the CIFAR10 test dataset. Now, instead of looking into one layer, let's look into the internal representations of two layers, which can be in the same model or across two different models. On this slide, I chose two layers, L2 and L6, in a given deep neural network model. Our goal is to compare the representations in those two layers and understand whether they learn similar or different patterns and how those similarity patterns change across different layers. Canonical correlation analysis, also known as CCA, can help us to explain the correlation between the representations of two layers. It is similar to PCA in terms of reducing the dimensionality, with a difference that instead of explaining the variance for one layer representation, it explains the covariance between two layer representations. On this slide, on my right side, we can see two top CCA directions that explain the highest correlation between layers L2 and L6. After computing CCA directions, we can compute the correlation among them using a simple correlation metric such as Pearson's linear correlation metric. SVCCA, singular vector canonical correlation analysis, is a further enhancement of CCA that applies CCA on the top directions of both layers that already capture the most variance. In order to identify top directions with the highest variance, SVCCA applies SVD to each layer representation independently. and then it applies CCA on the top SVD directions for each layer. Similar to CCA, we can then use a correlation metric that computes the correlation between the top CCA directions on each layer representation. SVCCA has some interesting properties. One of those is the invariance to affine transformations. This means that if we have two layers and the second layer is a linear transformation of the first layer, then those layers would still be similar, although the one is the transformation of the other. On this example, we visualize the similarity scores computed by SVCCA for two identical model architectures that were trained using different random parameter initialization. We can see that last and the first layers remain very similar for both models, while middle layers are less similar. In this example, we show how layer similarities change during the training when they are compared with the layers of the pre-trained model. For this specific example, a ConvNet model was trained using CIFAR10 dataset. We can see that lower layers successively become very similar to the pre-trained model as we progress in our training. This can help us to freeze certain lower layers in the early stages of the training and save computation costs. Projected weight canonical correlation analysis, PWCCA, is a further enhancement of SVCCA, which is better at distinguishing noise from signal. It is based on the idea of weighting CCA vectors based on how much they account for the original input vectors, as opposed to giving same weights to all CCA vectors. More details about this approach can be found in the papers linked on this slide. Now let's discuss the last approach on model comparison, centered kernel alignment. In contrast to previous approaches, centered kernel alignment, CKA, doesn't rely on the similarity between the CCA directions. It is based on the generalization of dot product similarity metric by kernel Hilbert spaces. In contrary to CCA-based method, CKA returns meaningful similarity score for representations with higher dimensions compared to the number of data points. Let's assume that X and Y represent the layer activations for L2 and L6 layers respectively. On the left side of equation 1, we have inter-example similarity defined by dot product that is equal to squared Frobenius norm of the dot product between X and Y representations. Equation 1 can be further generalized with Hilbert-Schmidt independence criterion for centered X and Y and redefined through linear or RBF kernel functions. In order to compute final CKA score, we normalize it, and this helps us to have invariance to isotopic scaling. Here we visualize some results from the original paper for two ConvNet models with identical architectures trained on CIFAR10 dataset with different parameter initializations. As we can see, both linear and RBF kernel return almost identical results. Also, along the diagonal, we observe high similarity score. In this example, we compare similarities between CCA, SVCCA, and CKA side by side. We would expect that the most similar layers would be the most architecturally similar ones. This hypothesis seems to hold for CKA, but not for CCA and SVCCA. It looks like, according to CCA and SVCCA, some of the architecturally similar layers are dissimilar. We don't see the same diagonal pattern with high similarity scores for CCA and SVCCA, but we see that for CKA. Identifying similar layers can potentially help us to better understand what our models learn. It can help us with transfer learning, model pruning, and freezing some of the layers during training, which in its turn can help us to save compute resources. Now let me wrap up the lecture by highlighting some of the topics that we discussed. We started this lecture with the introduction to model interpretability, explainability, and 5 desiderata of model interpretability, which elucidate specific areas that we want to focus on during interpretability research. Then we briefly talked about the differences between black box models and inherently interpretable models, and discussed gradient and perturbation-based attribution algorithms for explaining black box models in detail. After going over the theoretical analysis of explanation techniques, we moved to practical applications and showed how we can apply different types of attribution algorithms from Captum library to our classification and segmentation models. As next, we discussed the evaluation of model interpretations and explanations, concept-based model interpretability, and TCAF as a specific algorithm from concept-based model interpretability family. Lastly, we discussed different types of correlation analysis techniques and model comparison similarity metrics that can help us to visualize and compare different layers of our models. This lecture sheds light on some model interpretability and explainability techniques. However, it is by far not complete. There exist many other interesting research directions that I would encourage you to explore. Optimization-based visualizations and the research that looks into the relations between adversarial robustness and model interpretability are 2 of them. Optimization-based visualizations aim to visualize different concepts that a neuron or groups of neurons learn by optimizing an objective function for those neurons. On this slide, I have visualization of couple abstract concepts learned by different neurons. Besides that, in terms of adversarial robustness and model interpretability, it has been shown that vulnerability to adversarial attacks is connected to how interpretable gradients are. Robust models tend to provide more interpretable gradients and vice versa. So with this, I'd like to wrap up this lecture. I hope that the content was insightful and that you are excited to try out different types of model interpretability and explainability techniques for your machine learning models.